All right, in this video, we're going to look at the orthogonality properties of Legendre polynomials. We have done another video where we just looked at the property of orthogonality for functions in general. If you haven't watched that video, we strongly recommend that you start by looking at that video before you continue with this one. I'm going to post a link of it here just now. Right, so for Legendre polynomials, there are two properties that show their orthogonality. So the first one is that the integral of Pm of x times Pn of x dx. So this we mentioned in the video on orthogonality of polynomials, that this is just the inner product of the Legendre polynomials. So this property says this is going to be 0 whenever m is different from n. Okay, so that means Legendre polynomials are orthogonal in the interval -1 to 1 with respect to the weight function is 1 in this case. And then the second property says that the integral of Pn squared, so this is the case of P1 when the two subscripts here are equal. So this one is equal to 2 over 2n plus 1. This constant is called the normalization constant, because so we have Legendre polynomials. So the set of Legendre polynomials are orthogonal. We can convert them into a set of orthonormal functions, in which case we would have to use this constant here. All right, so what we're going to do is we're going to start by proving P1, and if time permits, we will go and prove P2 as well. But the proofs are a bit lengthy, so chances are we'll do P2 in a part 2 of this video series. All right, so for P1, we are going to start from the Legendre differential equation. Okay, so prove P1 by so we're going to start from the Legendre differential equation, which I'm sure you'll remember, 1 minus x squared y double prime minus 2xy prime plus n into n plus 1 y equal to 0. So the solution of this ODE is just going to be P of n. Now we use the fact that the first two terms can be written as the derivative of a product. So we're going to write that ODE like that. Okay, now, so what we're going to do is we are going to rewrite this in terms of Pn and Pm. So since Pn of x is a solution of this ODE, or satisfies this ODE, so Pn and Pm satisfy, so let's call this equation number 1, equation number 2, this one I'm going to call equation number 3. So since both Pm and Pn satisfy 3, then we can write the following ODEs. So 1 minus x squared Pn prime, so we're just going to replace every y by Pn for this ODE. And then for the second one, we're going to write exactly the same thing, but this time is the ODE for Pm. So all the m parameters are replaced, the n parameters are replaced by m. So we have got these two ODEs, so one for Pn and the other one for Pm. Then what we are going to do is we are going to multiply 4 by Pm. So we're going to multiply 4 by Pm, and we are going to multiply 5 by Pn. So we're going to multiply 5 by Pn, and then we are going to subtract. Okay, I'm going to subtract. So what's going to happen is the derivative terms are going to look as follows. So we're going to have Pm into 1 minus x squared Pn prime minus, so that's going to be the term from here now, Pn into 1 minus x squared Pm prime, and then these are the terms for the last two terms. I'm going to take them to the right hand side, so that means this term is going to be positive. So we're going to have m into m plus 1 Pm times Pn, and then minus n times n plus 1 Pm times Pn. So that's what we're going to have if we multiply this one by Pm, multiply this one by Pn, and subtract. Then we are now going to integrate from -1 to 1. So integrate from -1 to 1. So on the left hand side, we're going to have the integral from -1 to 1 Pm into 1 minus x squared Pn prime dx minus Pn 1 minus x squared Pm this time prime dx. And then on the right hand side, going to have m into m plus 1 minus n into n plus 1 times the integral from -1 to 1 Pm times Pn dx. Now the two terms on the left hand side are very similar in structure. Okay, the only difference is that the m and n are swapped. So what we're going to do is we're going to integrate this one by parts, and then the result is going to follow automatically for this one. Okay, so integrate by parts So we are going to integrate. So we're going to integrate this integral. So evaluate this one by parts. So what's going to happen is we're going to let u be Pm. So remember, Pm is a function of x, so du is going to be Pm prime dx. We're going to let dv be 1 minus x squared Pn prime dx, just this part of the integral. Then v is going to be 1 minus x squared Pn prime. Okay, so we are just going to do the left hand side. So the left hand side is going to be, so the first term is going to be, so this is going to be for the first integral, we're going to have uv. So uv is going to be 1 minus x squared Pm times Pn prime. We're evaluating this between -1 and 1. Take away integral of v du, going to be 1 minus x squared Pn prime Pm prime. So we're multiplying these v du, these two, then dx there, then minus, so these two terms are just for that integral there. So these two terms are for that integral there. Then we're going to have a similar type of situation for that second term. So we'll have minus, so this time is going to be 1 minus x squared Pn prime. Okay, so all that's going to happen with this term is going to be very much the same as this one, but the role of m and n is going to be reversed, and then this one is not going to be plus, because we're going to have minus 1 minus x squared Pn prime dx. So that's what the left hand side is going to be. Now the terms that we need to evaluate, so this one here, when x is 1 is going to be 0 on account of this term. When x is -1 is going to be 0 on account of this term. Same as this term here. And then what you notice now is that these integrals are exactly the same, but one of them is plus and the other one is minus. So that means the left hand side is just going to work out to 0. So then we just remain with the term on the right hand side. So on the right hand side, this is the term we have. So let's just work that out. I'm going to remove brackets in this square brackets there. So that's going to be m squared plus m minus n squared minus n into this integral here, Pn dx. So this is going to be m squared minus n squared plus m minus n, which we can factorize. So we're going to have m minus n into m plus n plus m minus n. So m minus n we can cancel out. So we're going to have m minus n into m plus n plus 1. Okay, now remember we have just found that the left hand side is equal to 0. So what this thing is telling us is that this right hand side must be equal to 0 as well. Well, how can this be 0? This one can not be 0 because m and n are positive. This can be 0 if m is not equal to n. So long as m is different from n, then the term that's equal to 0 can only be this one. And so that completes our proof. So so long as m is different from n, then the integral of Pm of x times Pn of x must be equal to 0. So that finishes off the first proof. Okay, in preparation to prove the second property, we are going to consider this integral here. So in is equal to integral from -1 to 1 of f of x times Pn of x. So actually the result we're going to derive here is going to be useful even for other evaluating other integrals of this form. Now using Rodriguez's formula, this we can write like this. So that's going to be f of x. It's going to be the nth order derivative of x squared minus 1 to the power n. Then we're going to integrate this by parts. So integrate by parts. So we are going to let u be equal to f of x. So du is going to be df of x df dx times dx. Then dv, we're going to have dv as the nth order derivative of x squared minus 1 to the power n dx, which means v is going to be the n minus first order derivative of x squared minus 1 to the power n. So in is going to be uv. So that is going to be f of x times the n minus first order derivative of x squared minus 1 to the power n, evaluated between -1 and 1. Then minus 1 over this 1 over 2n is also going to yeah, I'm going to sort that out just in a moment. So this constant multiplies everything, so if even this term here. So here we're going to have v du. There is v and there is du. So we're going to have df dx, the n minus first order derivative of x squared minus n dx. So the thing that I was talking about is that even here there's going to be 1 over 2 to the power n and factorial. All right, then we have got to evaluate this at 1 and at minus 1. However, since this order of differentiation is less than that power, that means this term here is always going to be a multiple of x squared minus 1. Maybe I'm going to demonstrate that there, but let's just write this out first. So since the order of differentiation, so the order of differentiation is n minus 1. Okay, so since this one is less than n, which is the power of that term, okay, then the first term, I mean this term here, will be a multiple of x squared minus 1. Okay, so there's always going to be an x squared minus 1 multiple there. And what that means is that when we evaluate this term at minus 1 and at plus 1, it is going to vanish. Okay, so the term vanishes at x equal to 1 and also at x equals to negative 1. Okay, let's just do a quick demonstration here. So I'm just going to imagine, let's take n to be 3. Okay, so that means n minus 1 is going to be 2. So that's 3 there. Then I'm just going to show you that that is going to be a multiple of x squared minus 1. So that is power 3 there. So if we differentiate this once, okay, then we're going to have d dx into 3 into x squared minus 1, subtract 1, then multiply by the derivative of the interior function. Okay, then now we're going to use the product rule. So if we differentiate the 2x, this is just going to be 6 into x squared minus 1 all squared. Then plus, now differentiate this and keep this fixed. So 2 times 3 is going to be 6. Then we've got x squared minus 1, subtract 1. Then multiply by 2x. So this is now going to be 4x squared. Now I can see that both terms have got x squared minus 1. So that derivative is a multiple of that. So just demonstrating that. So this term is going to be 0. Okay, so the integral is just equal to that. So therefore in is negative 1 over 2 to the power n and factorial into the integral of dx n minus first order derivative of x squared minus 1 to the power x. Okay, now what this means is that if we integrate in by parts n times, okay, integrate in by parts n times, we are going to get the following. So you're gonna notice that each time we integrate by parts, order of differentiation goes down by 1. But for this one it goes up by 1. So after n times it's going to be nth order derivative. This one is just going to be x squared minus 1 to the power n. So this is what in is going to look like. Of course, the sign here alternates, minus 1 plus 1, minus 1 plus 1. So we're going to have minus 1 to the power n over 2 to the power n and factorial integral from minus 1 to 1. Then we are going to have x squared minus 1 to the power n. So that is just going to be the polynomial. And for f, we are going to have the nth order derivative. So what this does mean is that, what this does mean is that the integral of f of x times this polynomial, what we will do is this term we can absorb into that polynomial there, because they're both to the power n. So then this is just going to be the integral, we've got that coefficient 1 over 2n times n factorial, the integral from minus 1 to 1. So this is going to be 1 minus x squared to the power n, then nth order derivative of f times dx. So this is going to be a very useful result going forward. Now for P2, so remember P2 says the integral of Pn times Pn, I'm just going to write it like this, is equals to that. So if you compare this integral with this integral, it means here f is equal to Pn. So that's exactly how we are going to proceed. So for this P2, we have f equal to Pn. If we write this using Rodriguez's formula, just the nth order derivative of x squared minus 1 to the power n. Now in this formula, we're going to need to differentiate f n times. So that means that nth order derivative of differentiate this n times, it's just going to be, so let me do this like this, x squared minus 1 to the, so it's simply going to be 1 over 2 to the power n factorial. Then this is going to be the 2nth derivative of x squared minus 1 to the power n. Now the degree of this polynomial is 2n, so if you differentiate it 2n times, we're just going to find 2n factorial. So that's what that is going to be. You can actually prove that this result or this term here is equal to that term there by mathematical induction. So what we're going to do is we're simply going to take this this term here, and we're going to plug it there. Okay, so so let's say thus we have, so our in this time, remember, is this term there. So our in is going to be equal to 1 over 2n and factorial integral from 1 minus 1 to 1 minus x squared to the power n. Then we're going to have 2n factorial all over 2n times n factorial dx. Then if we take the constants outside, then this is going to be 2 to the power 2n is going to be n factorial squared negative 1 to 1 1 minus x squared to the power n dx. So all that we need to do here is to evaluate this integral, and then hopefully we can show that this thing is equal to 2 over 2n plus 1. So let's work with that integral there. So that integral got minus 1 to 1 of 1 minus x squared to the power n. Since the integrand is even, we are going to write it like this, and then we're going to introduce a substitution, convert this into a beta function integral, or maybe not. Oh yeah, yes. All right, so so if we let u be equal to x squared, then x is square root u, and dx is du over 2 square root u. So the integral is going to be, there is that 2 there, the limits remain the same, so this is now 1 minus u, then I've got du over 2 square root u there. These 2's cancel out, so we are going to have the integral from 0 to 1 of u to the minus half 1 minus u to the power n du. So this is like in the standard beta function form. So it's just going to be the beta function of 1/2 and n plus 1. Gamma function of 1/2 is that, and gamma function of n plus 1 is n factorial. Then in the denominator we're going to have n plus 1 plus half. So this is the same as if we use the recurrence relation for the gamma function. That's going to be n plus half into the gamma of n plus half. The gamma of n plus half we can evaluate using something called the duplication formula. So let me just put that one here. So the duplication formula says that the gamma function of n plus half is equal to the square root of pi times the gamma function of 2n divided by 2 to the power 2n minus 1 times the gamma function of n. So we're going to take this thing and plug it in there, and then that's going to enable us to work out that integral. So going back to this, so that is going to be square root of pi times n factorial divided by n plus half, and then times square root pi, maybe let me just write that one here, square root pi, then gamma function of 2n is 2n minus 1 factorial. Then in the numerator we're going to have 2 to the power 2n minus 1. Then gamma of n is n minus 1 factorial. So we're just going to work this out to the end, because the result of this integral as well, we are going to find that we need it a few times going forward from here. All right, so what we are going to do is let's just see if anything cancels out, and indeed square root pi cancels out. Then we're going to take these two and multiply into that term there. So in the numerator, we're going to have n factorial, n minus 1 factorial. This becomes 2n plus 1. Then we have here 2n minus 1 factorial. We're almost there. Now, oh, and then there is the 2 to the power 2n, which is this one there. Right. The term in the denominator, this one here, is almost 2n plus 1 factorial. Only if we had 2n here. So what we're going to do is we're going to plug in that 2n there, and then that's going to help us write this in a much a more elegant way. So we'll put 2n here. So that means we need a 2n in the numerator as well. With that, the denominator is now 2n plus 1 factorial. 2n plus 1 factorial. The numerator, these two, we're going to absorb into those factors of 2. This n, if you plug in that n here, so actually n times n minus 1 factorial is n factorial. So we're just going to have 2 of those. So that term is going to be, the numerator is going to be 2 to the power 2n plus 1 times n plus 1 factorial. So we're now going to go back. So remember, we got here because we were working with that. So we're now going to go back to in. So we're going to say in is equal to, we've got 2n factorial over that. So 2n factorial divided by 2 to the power 2n, n factorial squared. And then the integral, which is what we were working out, is giving us this term here. So that's 2 to the power 2n plus 1, n plus 1 factorial squared, 2n plus 1 factorial. So some of these terms are going to cancel out straight away. That cancels out. Then this cancels out, but we're going to remain with a 2 in the numerator. Okay. And then this divides into this, and the quotient is 2n plus 1. And so we have got our result. All right. Yeah, so that was a bit long, but hopefully you did manage to follow through. Thank you for watching. Hopefully this video is useful to you. Please do subscribe. If you've got comments, you can put them in the comment section, and you can share the link to this channel to people that you know will find this useful. Thank you.